Hello everyone, today we will work on exercise set 16.5. Before we really start, let's remind ourselves of the topics here, the discussions here. The first one, let's define a vector field F. Let vector field F be a three-dimensional vector field, P, Q, R, each of them a scalar function with, and I think I should say, and PQR have first partial derivative exists. I think with first partial derivatives exists for each of them, and then by definition, divergence of vector field F, also denoted gradient dot F, that's basically dou x, dou y, dou z of PQR. That is the partial of P respect to X plus partial of Q respect to Y plus the partial of R respect to Z. So it's the sum of the partial derivative of each component respect to its position. Okay, that's for divergence of F. And then the curl of vector field F is the gradient cross F, which we can see as, if we write that using determinant, that's the ijk in the first row, the second row dou x, dou y, dou z of PQR. Okay, that will give us dou r dou y minus dou q dou z. For the second component is negative of dou r dou x minus dou p dou z. And the third component is dou q dou x minus dou p dou y. Now, if you remember Green's theorem, is basically having the third component in the integrand and the first two components equals to 0. Okay, because the Green's theorem assumes that our vector field is only two-dimensional, which we can see as PQ0. Okay, and the PQ each function of x and y only without z. Okay. Now, of course, one of the reasons I mentioned this now is because later on we can actually apply Green's theorem if we have the vector field on yz only or xz only, if you are missing one of the variable. Okay, on a flat plane, let's say on xz plane, for example. Okay, and then the y is 0. The q component, the PQR, the q is 0. Okay, now furthermore to say is that definition, not a nice color, definition vector field F is incompressible if the gradient, the divergence of F is 0. Basically, it doesn't expand, it doesn't compress. It's not, you cannot, the fluid is not expandable and not compressible. Okay, another one is the vector field F is irrotational if the curl of F is vector 0. Okay, and well, the vector field is also said to be conservative. Okay, yeah. What else to say? Oh, another one is that the divergence of the curl of vector field F is equals to 0, and this is due to Clairaut's theorem. Clairaut's theorem. Oh, but of course this requires the second partial derivatives to exist. Okay, let me write that as a note. This requires second partial derivative of PQR to be continuous. Okay, therefore Clairaut's theorem apply. Okay, that's basically what we really need from this section. Let's see. From 16.5, I saw from my lecture videos I don't really do problems from this section because I think it's on the easier side. Okay, so if that's the case, let's see which problem I would like to go over. Let's do number 4 and 8 from here. Okay, find the curl and the divergence. I will do divergence first. I think that's on the easier one. So number 4, we have vector field F to be sine yz, sine xz, and sine xy. So the divergence of F, that's basically the gradient of vector field F. That will be the P derivative respect to x, that's 0. The Q derivative respect to y, that's 0. And this, oh, this is 0, huh? Oh, okay, that's the divergence. How about the curl then? The curl of F, which is the gradient cross vector field F, that's I j k of dou x, dou y, dou z of P Q R. Let me move this a little bit to the right. And this will be, the first component is, derivative of sine is cosine x cosine xy, right? Minus x cosine xz. That's the first component. The second component will be negative of y cosine xy minus y cosine yz, comma, the third component will be z cosine xz minus y, oh, sorry, minus z cosine yz. Okay. I wonder if we can simplify that, but apparently not, huh? Yeah, I don't think we can simplify that. And at most, I can factor the x in the first component. Cosine xy minus cosine xz. And in the second component, I can factor the y, and that refers the order of subtraction. That's cosine yc minus cosine xy. And then c cosine xc minus cosine yc. Okay, that's the curl of vector field F for number 4. Let's see number 8. Number 8, the divergence of F the derivative of the P respect to X plus the Y, the Q respect to Y, and then the R respect to Z. Oh, that's what we get, huh? I will just leave it like that. I think that's simple enough. Okay, and how about the curl of F? That's ijk do x do y and do z of p q r. Okay, how about the x component? That will be 0 minus y to the negative, that's plus y over c squared. The second component, that's negative z over x squared minus 0. Is it right? And then the third component, that's 0 minus negative x over y squared. So if I clean up, this is y over c squared, z over x squared, x over y squared. Okay? Why I feel number 8 is easier than number 4. Okay, that's just about the curl and divergence. Let's go on. Determine whether or not the vector field is conservative. If it is conservative, find the function, find the potential function. Okay, which question should we do? Let's do number 14 and number 18. Number 14 first. Let me do it here. Number 14. So we have vector field F equals to x, y, c squared, x squared, y, c squared, and then x squared, y squared, c. So to show that it is conservative, we need to see if the curl of that vector field is equals to 0, which means it's conservative because it is irrotational. Okay, think of it this way: the reason that the force then becomes the force field is not conservative because some of the force being used to rotate the point on the path, while it is conservative if there's no force, therefore no work being used to make that rotation. Okay, so basically a force field becomes not conservative if some of the force being used to create rotation. Okay, curl of F will be I J K for the first row, the second row dou X, dou Y, dou Z of X Y C squared, X squared Y C squared, and then X squared Y squared Z. That will give me 2x squared yc minus 2x squared yc, comma, negative of 2xy squared c minus 2xyz. It's not, so it is not. And then this will be 2xyc squared minus x c squared. Okay, the first component is 0. The second component is not though. This is 2xyc minus 2xy squared c. And then the third component also not, which is not factor 0. So for number 14, the force field or the vector field is not conservative. Okay, that's for number 14. Let's see number 18. The vector field is e to the x sine yc, c e to the x cosine yc, y e to the x cosine yc. Okay, why I suspect this is also not conservative? I don't know, I have to work it out, but I have the feeling that it is not. E to the x sine yc, z e to the x cosine yc, and then y e to the x cosine yc. Let me continue on the right hand side. So the first component will be e to the x cosine yc plus y e to the x negative z cosine yc. Am I right? Hold on. Oh, not yet. I'm not done yet. Minus 3 with respect to z, there will be e to the x cosine yc. And then minus yc, it should be sine, not cosine. It should be sine here. E to the x sine yc. Oh, that will become 0, That's the first component. Let's see, the second component will be negative of respect to x, that will be y e to the x cosine yc minus respect to z here, that will be ye to the x cosine yz. Oh, that's also 0, huh? I don't need this part. And then the third component, that will be, that's the middle one. Okay, so the third component will be e to the x cosine yz minus z e to the x cosine yc. Hey, they actually cancel out, huh? Surprise, surprise, surprise. So this is the curl of the vector field is 0, so that vector field f is conservative. I was not expecting this. Now, because it is conservative, then we need to find the potential function. Okay, so let's go back. Because it's conservative, let f x y z be the potential function, or simply called potential, of that vector field. Basically, so the gradient of f equals to that vector field. Okay, now that means the p is equal to the partial of f respect to x, right? That implies the function f is the integral of p respect to x. Okay, that's the integral of e to the x sine yc dx, that is itself, right? Plus, call that g1, which is a function of yc. Okay, well, because this function f, if we do the derivative respect, if this function we do the partial respect to x, this will disappear, right? Okay, so when we do the integral, we anticipate we may have a function depending on yc only. Okay, now the q component, the second component, is the partial of f respect to y. So the function is integral of q dy. That's integral of z e to the x cosine yz. If we integrate respect to y, that will be e to the x sine yc, Don't you think so? If you do the derivative of that respect to y, you will become cosine with extra coefficient z, right? Of g2 of xz. Finally, the third component r, that is the partial of f respect to z. Therefore, the function must be integral of r dz. That's integral of y e to the x cosine yc dz. Oh, that's the same thing, huh? So we don't have other function, basically. So the potential function f x y z is e to the x sine yc plus constant. Okay, the function that is a function of yc, function of xz, and function of xy at the same time must be just that constant. Okay, that's the potential function. That's for number 18. Let's go on. We get into some theoretical questions here. Number 20. Is there a vector field G such that the curl of G equals to that. Suppose, number 20, suppose G is a vector field that's PQR such that the curl of G is equal to xyz negative y squared z yc squared. Now suppose we have such a vector field G, not F, sorry. Suppose we have such vector field G. Now notice that all this part here, the x, y, and z component are all continuous, right? So if we apply the divergence of that curl of G, okay, it's supposed to be 0. Okay, based on this theorem here, the divergence of the curl supposed to give us 0. Okay, but when we do divergence, we get yc minus 2yc plus 2yc. Okay, the partial respect to x. Then we continue. We get yeah, this is the partial of this respect to x. Oops. And this is not equal to 0, right? From there, we see that, but divergence of curl of G, knowing that it has a second partial derivative exists, is supposed to be 0. Okay, so there is no such G. Okay, that's for number 20. Number 21. Show that any vector field of this form, so vector field of the x component is a function respect to x only, depend on x only. The y component is a function respect to y only, and then the c component is a function depending on c only. Show that it is irrotational. If we have such vector field, show that it is irrotational, which means the curl, we need to show that the curl is 0. Okay, so I, j, k, do x, do y, do z of f x g y h z. Now you see that the curl becomes 0 because when you do the partial, you do partial with respect to a variable that it is not depending on. Okay, so for example, the first component here will be dou h, which depend on z respect to y. You know that will be 0, right? Okay, minus the partial of gy respect to z. You know that will be 0, right? That's 0, 0, 0. Which is a vector 0. So the vector field is conservative and therefore is irrotational. Okay, that's for number 21. Number 22, show that this function here is incompressible. If the function in the x component depends on variable non-x variable. The second component, the y component, is a function depending not on y, and the c depends on a variable not z. Now then you will see the divergence of f, this is number 22, the partial of f respect to x, that will be 0. The partial of g respect to y, that will also be 0. The partial of h respect to z, that will also be 0. Okay, because the divergence of that vector field is a scalar 0, therefore that vector field is incompressible. Okay, that's a very theoretical question though. Okay, number 30, I think this is the last question. Number 30, verify each identity. We have that factor r, which is x, y, z, okay, and that r without the arrow, so the scalar r is defined to be the magnitude of factor r, that is square root of x squared plus y squared plus z squared, right? Okay, verify each identity. Part A, what is the divergence of factor r? Divergence of factor r will be dou x respect to x, and then the second component y respect to y, the third component z respect to z, that's 1 plus 1 plus 1, that's 3. Oh, that's Mickey Mouse. Part B, how about the divergence of r times factor r? This is a bit challenging. This is basically the divergence of r is square root of x squared plus y squared plus z squared of that factor x, y, z, right? Okay, which is basically we need to find the divergence of this big factor here, x square root of x squared plus y squared plus z squared. That's for the x component. The y component, y times square root of x squared plus y squared plus z squared, and then the third component, c times square root of x squared plus y squared plus z squared. Okay, now then the first component, when we do the partial respect to x, that will be square root of x squared plus y squared plus z squared. We need to do the product rule, right? Plus x times the derivative of that square root something with respect to x. That will be 2 square root of x squared plus y squared plus z squared on the denominator. On the numerator we have 2x. And we do likewise for the y and the z component. Okay. What I want to show you is that the first part here we will get square root of x squared plus y squared plus z squared plus x squared over square root of x squared plus y squared plus z squared. And of course you will see that the y and the x component, the partial respect to x, I'm sorry, respect to y, the partial respect to z component will follow similar pattern. Okay, this will be r as a scalar plus x squared over r plus. Later on, let me change the color. This is the red one, and the red one will becomes r plus y squared over r, and then the C component, you try to do it, okay, work it out. That will be R plus Z squared over R. Now, putting things together, we get 3R plus X squared plus Y squared plus C squared over R. But X squared plus Y squared plus C squared, as we know, is R squared, right? That's 3R plus R, which is 4R. So that comes out to be the same to what they want us to show. Okay, that's for part B. Now let's see part C. Part C, we have the partial, oh, this one, the partial, oh, what happened? Gradient squared R cubed. How to explain this? Gradient squared is the same to the divergence of the gradient of R cubed. That's what it means. Okay, and thinking about it, I hope you see that makes sense, because A dot A, that's the same to A dot A is the same to the magnitude of A being squared, right? Okay, it gives you a scalar. It gives you a scalar. Okay, I'm referring to this. I'm referring to this guy here. We see that as this way. Okay, if you have a scalar function coming after that. Okay, now what does it mean? It means I need to find, let's express that R cubed first. R cubed is x squared plus y squared plus c squared to the power of 3/2. Right? Now, the gradient of that will be, then it becomes a vector field, right? It will be 3/2 x squared plus y squared plus c squared to the power of 1/2 times 2x for the x component. For the y component will be x squared c squared 2y, and then for the c component similarly will be to the power of 1/2. This then the divergence of x 3x times x squared plus y squared plus c squared to the power of 1/2, 3 times y, x squared plus y squared plus c squared to the power of 1/2, and 3z of x squared plus y squared plus c squared to the power of 1/2. Actually, you notice that we can factor the 3 out also, right? Okay. Now, but the divergence of that will be, I factor the 3 out, but then for the x component, I need to do product rule, which is x squared plus y squared plus c squared to the power of 1/2 plus x times, the derivative of that will be 2 x squared plus y squared plus c squared to the power of 1/2 on the denominator. On the numerator we have 2x. Okay, and then plus, I'm sorry, it's not a factor anymore, plus, let me change the color, the similar thing, plus the similar thing. Okay, you work it out. Now what I want to show you is that the first term here, that's r, plus 2x squared over, I'm sorry, the 2 cancels, huh? over x plus x squared over r. And then for the y component, you will see this is r plus y squared over r. And then for the c component, you will see r plus c squared over r. If you think about it, this is basically, hold on, why I feel like we did it before, huh? Don't you think so? Well, anyway, I just realized that too. This is basically the same to 3 times the gradient of the gradient dot. This is r, right? See, if you, how to say that? How to say that? Let me do it slowly. Let me do it slowly. So if I factor the 3 out, I get 3 times the divergence of x times r, y times r, z times r. But that's equal to 3 times the divergence of r factor r, which we have done in part B, right? That's 4r. Okay, so yes, we did show that it's the 12r. Now you can also go on from here. If you want to continue from here, then you will get 3 times 3r plus r squared over r. That's 3 times 4r. That's 12r, right? Okay, but I just realized that we basically repeat what we did earlier in part B for this part C in between. Okay, now this is 4 problems from 16.5. I hope you do find this section to be on the easier side.